Welcome back to the second half of our machine language coverage. Thus far, we've seen what instructions look like in machine language, but this still wasn't the whole story. The instructions we've seen only had references to other locations that were known at assembly time. For example, a jump to a label that is 4 instructions later. That won't always happen. For instance, with a call to a library function like printf. We know from earlier in the course that this is where the linker comes in, but now we'll actually get to see how the assembler lets the linker know what it needs help with, and then what the linker actually does. To dive into this, we need a program to study. Here's a program that prompts the user to enter a character, then checks if the character entered is capital A, and prints hi if it is. The program isn't that interesting on its face, but let's look at the assembly version, which references labels within our text section, within another section, and in the text section contained in another file that we don't have access to at assembly time. In the RO data section, we have a prompt string followed by the hi message string. Then we go to the text section, and after our prologue, we have an ADR of one of those strings, then a call to printf, which is, of course, found in an external library. We also have a call to getchar, again from an external library. Then the conditional branch jumps to another spot in our own text section. There's another ADR referencing our RO data section and another call to printf. After the skip label, there's the conventional setting of the return value and the epilogue and ret instruction. So now we have to answer the question what the assembler does to generate machine language for this, when it doesn't know the addresses or offsets of several of these references. We can see exactly what the assembler generates in a .o file by using the objdump command, which will potentially prove useful in assignment 5. Perhaps surprisingly, we don't actually see any addresses here. We see that RO data starts at 0. Surely that's not a valid address. In fact, using only what we've learned in the class, we can prove that this can't be an address. String literals are in RO data, and we can dereference them, for reading only, of course. But we can't dereference null pointers, which are pointers that point at the address 0. Thus, this 0 annotation here better not be an address. And indeed, it also makes sense for another reason. We've learned that finalizing the address of each section in the executable is the linker's job. But now, if we think about it, we can reason that the assembler can't do it. Consider if you have a module like your string or simtable or begint add. There's no way the assembler can possibly know when creating straw.o or simtable hash.o or any of the other implementation object files. It can't possibly know what clients will end up using them. That means it can't finalize any of the addresses for things in your module, because if it did, that would risk a conflict if the assembler for the client or for another module in the client's program put something else at that same location. So at this point, we can't have addresses, but we can have offsets, displacements from other things. In this case, the start of this file's entries in RO data, which will eventually be combined with other files' RO data sections. The assembler has enough information to know type a char is the first string in this RO data section. So let's call that offset 0. And hi is the second string, coming right after that. So since the prompt string has 14 characters, remember the null byte, hi can start at offset 14, or hex E. With a different set of command line arguments, objdump can also show you the text section. It'll even do the disassembly for you so that you can read your previously dreaded but now super comfy assembly language rather than having to read the machine language directly. Note, though, that the machine language is there. The 8 hex digits are a compact way of representing the 32 bits of the instruction, so you can, if you want or need, expand these out to get the full 32-bit strings for the instructions, just like we saw last lecture. We'll dive into the actual instructions in a second, but first let's look around at that first column of the output of objdump. Just like with the RO data section, the assembler can't generate actual addresses for the instructions. The reasoning is the same. If the .o files had the addresses, then there would surely arise conflicts where, for example, the assembler puts some local function in detect.a.o in the same location that an assembler way back when put printf in stdio.o. So these are just offsets. We're counting by 4 because each instruction is 4 bytes. When we have a label like main or skip, it appears to have an address, but again, it's just the offset. So now let's look at each of these instructions one at a time. At offset 0, which is to say the beginning of the text section from this source file, we have the beginning of main's prologue, a subcommand to make space for main stack frame. When we expand out the hex of the machine code, D to 1101, 1 to 0001, and so on, we see each individual bit. But of course, you aren't expected to remember all the components of the instruction. Perhaps at best, I can hope you remember that the last 5 bits are the destination register. And yeah, those in fact do look right. 5 ones makes 31, so that's SP. It would be handy though if I could pull up the formatted slides from last time. So let's do that. Here's what a sub looks like, primarily as a reminder from last time. The operation group bits with the full opcode in burgundy, the instruction width, whether to use a 64-bit or 32-bit registers in pink, the determiner for whether or not the instruction sets the condition flags in p-state in cyan, the second source operand, which is an immediate in this case, in orange, the first source operand, the register SP in green, and as noted before, the destination, also SP in blue. So far so good, exactly like we saw on Monday. The next instruction was the second part of the prologue, stashing the value of x30 onto the stack so that we can recover it to be used by the ret instruction at the end. Again, nothing new here. We're storing an 8-byte value, so the width is 1, 1. We're storing it to the location SP points to, not to an offset, so the orange offset is 0. This is a store, so the usual semantics of source and destination are flipped, and thus we're storing x30 in blue into the location that register SP points to in green. The third instruction is the ADR to get the prompt's address into register x0 in order to pass that to printf. But this is weird. It says main here, not message 1. Recall that ADR was a bit funky with the disconnected relative address, the more significant bits of the relative address in orange, and the disconnected from them the least significant bits of the relative address in green, closer up to the most significant bits. But okay, let's parse it out. The opcode is normal, the destination register is 0, which corresponds to x0, so that's good. But when we put together the two parts of the relative address, we get 0. But if it's 0 bytes away from this instruction, doesn't that make it this instruction? But this instruction isn't the prompt. This is in fact a placeholder text left by the assembler, because it can't finish the job here. Message 1 is in RO data. This instruction is in text. The assembler has no idea where those two sections will go in the final executable, so it can't know the distance between this instruction and that label. Thus, it just leaves zeros as a placeholder. It will also need to leave a message for the linker to say, this is just a placeholder here. When you figure out the location of RO data and of text, can you do the subtraction for me and fill it in here? Thanks. Going back to the output from objdump, perhaps you've noticed that we've been ignoring a bunch of lines, going so far as to gray them out on each slide. Let's look at them now. There are, after some instructions, annotations that list the offset of the instruction and some other information. These are relocation records, which are annotations that the assembler leaves for the linker, plaintive calls for help, if you will. Here's our first one, corresponding to that ADR. It's a bit cryptic. We see the 8 is the offset of the ADR instruction that the assembler couldn't finish. We see some big string that has AART64. Okay, that's the ARM architecture, and ADR, which probably means the address, or maybe it's affixed to the ADR instruction or something like that. And some other substring that doesn't mean much to us. And then we see .rodata, the section that the assembler didn't have enough information about. So there are a lot of sensible pieces here, but we can't pull it all together. Here's how we can interpret the relocation record. Again, it's a plaintiff plea from the assembler to the linker. So let's imagine it as a sort of requisition order. 8 is the offset in the text section that contains the instruction that needs to be fixed once the linker's figured out where to put stuff. ART64 is the architecture. It's asking for an address relative to this instruction. What's this instruction? Well, it's the value of the program counter when this instruction is going to be executed. It notes that there's room for 21 bits of that relative address in this instruction. And it's noting that the ROData section address is the address that's going to be needed, in addition to the address of the text section where this instruction will be. We could note ROData plus 0, since we're not looking for the ROData section itself per se, but rather the address of message 1, which is the 0-byte offset into it. But anything plus 0 is itself, so .ROData it is. This is all the information the linker needs in order to fix up the instruction into its final form for the assembler. Okay, 1 relocation record down, 4 more to go. Our next instruction is the BL call to printf. Now that we know a little bit about placeholder data and instructions, we can see that this is going to have it. Branching to memory location 0 isn't going to be a thing. Let's look. Indeed, we have an opcode for BL, and then an entirety of the relative address is 0. The assembler needs to calculate the relative address between this instruction and printf, but it doesn't know where printf will be. It's off in another file. The linker could choose to put it anywhere. Before this, after this, who knows? Printf's label is needed to compute the relative address, and it won't be here until the linker does its thing and gathers up all the functions referenced to shove them together into a unified text section. So the assembler's stuck. It's forced to fill in a placeholder of 0. And now it will tell the linker what it has done and how the linker can fix it with another relocation record. As predicted, here is that relocation record. Let's dive into it again. Again in the form of a prim and proper written correspondence, for consistency and because, why not? Let's go step by step again to interpret the relocation record. C is the offset in the text section in this object file that contains the instruction that needs to be fixed once the full text section locations are finalized. Again, we have the architecture. It's asking to fix the relative address in a function call, which consists of 26 bits. The function it needs the address for is printf in order to subtract that address minus this instruction's address. This is actually now all the information that the linker needs in order to help fix up the instruction into its final form for the assembler. So now we're 2 relocation records down, and we've seen the 2 main forms that that we're going to see. So the hard part's behind us. Everything now is going to be just variations on the same theme. We turn around from calling printf and immediately call getchar. Again, that 0 portends that the assembler can't finish the job here either. Again, with a BL, we have a 26-bit relative address that the assembler fills in with all zeros, just like for printf. And again, the assembler will leave a love note for the linker asking that it patch the proper 26-bit relative address between the final address of this BL instruction, the one at hex offset hex 10, and the address of getchar, wherever those 2 addresses end up being. After the call to getchar, we have to figure out whether we read A or not. We'll do a comparison between W0 returned by getchar and the immediate value. In this case, hex 41 is the ASCII code for a capital A. It's decimal 65. Perhaps you recall from a few lectures ago that CMP is really just a convenient, semantically meaningful alias for subtraction that sets condition flags and throws away the result. So when we look at CMP, the opcode is actually that of subtract. In this case, subtract and immediate. It's a W register, so the width is 0 for 32 bits. The cyan bit is bit 29 is a 1 for yes. That's the whole point of CMP, is to set the bits of P state. The sources are the register 0 and the immediate value hex 41. And because setting the bits is actually all we want to do, we're happy to throw away the result, so the destination register is WZR, the always 0 register, which will happily be written to without changing its value away from 0. Note that this instruction uses 31 for WZR, as opposed to some of the others we've seen that use 31 for SP. This came up on a Piazza post in the last lecture. You can go and check out the very first ARM precept handout to see which instructions use 31 for the stack pointer and which use it for the always 0 register. The next instruction is another branch, but this time it's not a BL calling some external function. Instead, it's a conditional jump to another spot within the text section that's defined in this file. In terms of the C code, it's saying, if we didn't read in A, don't print high. For this instruction, the assembler has what it needs to complete the instruction. It will be exactly as we saw in the last lecture. We know the offset of this instruction, and we know the offset of the skip label. Well, the text section instructions from this file aren't going to just get sliced and diced and thrown in the air and mixed up. They will not be rearranged in the final executable. They're just going to be plunked down as one of several coherent code blocks. Thus, the difference in the offsets will also be the difference in the addresses. The assembler does the equivalent subtraction that it can, based on the offsets, and completes the instruction with no further help required from the linker, and thus no relocation record. But now we see another ADR, and again we're going to get the address associated with the label in the RO data section, so that's going to require the linker. So we again ask the linker, in perhaps a little bit more modern parlance, hey, at offset 1C, I can't quite finish this. When you figure out where you're going to put my code as part of the RO data section, can you add offset E to that address, subtract that and the address where you put offset 1C, and fill that into the instruction. Okay, thanks, bye. The last instruction the assembler needs help with is like the previous function call. Another BL instruction with its relative address filled in with placeholder zeros, pending the linker reading the corresponding relocation record and finishing the job with printf's address. We finish off with 4 more instructions, all of which the assembler can handle by itself. Don't get scared with all those zeros in the instruction at offset 24. We're dealing with register 0 and immediate value 0. Those aren't placeholder data, those are actually the values. For further practice, you could, in principle, do the exact breakdowns that we've been doing for in all of these slides for these instructions. All right, so we finished off the assembler. Now onto the linker, which now, in addition to all the jobs we knew it had to do, we've also added even more, namely dealing with the relocation record request from the assembler. The linker takes as input all of the .o files created by the assembler for all the files in the program and combines them together. The linker has 2 phases considering the merged data from the .o files. Resolution, which involves resolving references, and relocation, which involves moving code around and fixing the instructions to have actual relative addresses, not just offsets. With these steps, it eventually produces the final executable. In the resolution step, where we're resolving references, let's think about one specific example of doing so. The linker will notice that some BL instructions have a reference to a label that doesn't actually exist in any of the program's text sections. For instance, getchar or printf. It will fix this by going out to libc.a, which is just a big archive file made by the R command, kind of like a tar file except with no directory structure, and finding the corresponding .o file within that archive. It will take that file, which contains the machine code, and then add it to the combined text section. The second linker phase is relocation, moving code around, because after all, your text section started at offset 0, and libc's text section started at offset 0, but only one of you can actually be at offset 0 from the beginning of the final text section. So then, once things are in place and everything's been moved around so there are no conflicts, and we know the final addresses, now the linker has to go through and fill in the missing numbers of relative addresses from the text section to the RO data section, or to the new additions to the text section. Once it's done all of this for all the object files, fixing up all the things that the assembler left for it, it packages up the final result into the Linux executable file format and completes its work. Just as we could use objdump to look at an object file's contents, we can also use it to look at the final executable. And when we do, we see actual addresses. For example, starting at 400710, not offset starting at 0 from the beginning of the RO data section. Similarly, we can also use it to look at the final executable and the text section, and when we do so, we again see actual addresses. Recall that skip was hex 24 ahead of main when it was offset 24 and main was 00. Now we have a full address for main and a full address for skip, but the address for skip is still hex 24 higher. This was why our branch instruction worked without having to get the linker involved. There's also additional code beyond the code we wrote. Well, some of this we already talked about, how the linker will have dragged in the machine code for printf and getchar. But it will have also at that step given us code for _start that calls main to start our program, and assorted other functions from the C runtime framework. Also now there are no relocation records left. Much as T.S. Eliot wanted to have it happen, but Firestone Library is super happy that Emily Hale didn't do, the linker has burned all evidence of the assembler's communication with it. It leaves only the finalized instructions. When we look at ADR and see an absolute address and a note that this is message 1, no longer 0 and main. We look at the BL and see an actual address in the assembly and a note that this is printf. It's looking good. But let's dive into the machine code one last time just to see the final result. First, for an ADR instruction to get the address of a string in the RO data section, we now know that current instruction's address, visible here, and we saw earlier that message 1 was at 400720, so we can do the math and get that the former is C8 after the latter. Does the instruction match? We do the concatenation of the green onto the end of the orange, and indeed the relative address is C8. Similarly for BL, the assembly for the instruction lists an actual location in the new combined text section. When we look at the bits, we see a gigantic set of leading ones in the relative address. But since this is 2's complement, so this is just a negative number, it's the negative of 1011111. But remember to shift left by 2 bits to restore the bits that we could omit because of the alignment guarantee that we talked about last time. So this is actually negative 101, 111, 100. So the negative means the location we're jumping to is before the current instruction by hex 17C. And this is indeed what the subtraction of 40065C minus 4004E0 would give us. The rest of the instructions are more of the same. We no longer have offsets, we have addresses. We no longer have placeholder data and relocation records, we have fully fledged, ready to run instructions. This finally closes the book on the 4-stage build process that we've been talking about since literally the first class. And with a thorough understanding of what's going on at the machine code level, you're now ready to go off and write the mini-assembler portion of assignment 5 in order to generate the machine code for the assembly statements you want to inject into the greater program. This also completes our language level tour. Now we'll return primarily to C code and begin a new downward tour, starting back up at our comfortable C application programs and peeling back the onion towards the raw services the OS provides.